Welcome to this second half of today's lecture, and in the last half I have left two implications to prove. We will finish those implications now. So, proof of 1 implies 2, this was left, so we will do that now. So, one was x is so given, suppose that x is integral over a, that is it satisfies the monic polynomial with coefficients in a, that is x power d plus ad minus 1, x power d minus 1, etc. plus a1x plus a0 is 0 with d is some integer, natural number, and a d minus 1, etc. ad a0, they are elements in the ring A. This is what I have given, and what do you want to prove? So, I will write in here to prove that the subalgebra of B generated by X, that is this, is a finite A module. That means we want to find a generating system for this module, and that should be finite. So, in fact we shall prove that this subalgebra AX is generated by 1 2. So, it is generated by a times 1 plus a times 1 a times x plus a times x power d minus 1. That means this equality means every element here is a linear combination of 1 x up to x power d minus 1. So, this means, so that is 1 x power d minus 1 is a generating system for the A module AX. Once we prove that, then we are done. And how am I going to prove this? I am going to prove this by induction. So, we shall prove this, by induction on M that x power m belongs to A plus ax, etc. plus a x power d minus 1. This is what induction on M. So, that this. Alright. So, for m equal to d, this m equal to if m were smaller than d minus, smaller equal to d minus 1, there is nothing to prove. So, clear for m less equal to d minus 1, and for m equal to d, it is given this equation, I will just rearrange it. So, it is given by the definition of integral element. Alright. So, now I have to prove it from inductive step only, from I will assume for m and prove it for m plus 1. Alright. So, So what do is you have given, assume x power m belongs to a plus ax plus ax power d minus 1. So what does that mean? So this is given to us by induction hypothesis. And what do you want to prove? The next one. But this is given means what? That means x power m equal to some b0 plus b1x plus b d minus 1 x power d minus 1 with b0 etc. b d minus 1, they are elements in A. Now multiply this equation by x. So multiplying by x will get x power m plus 1, which is equal to b0x plus b1x square. You can go on till b d minus 2 x power d minus 1, and the next one is bd minus 1, and this d minus 1 multiplying by x will become xd, and from there, from this integral equation, I will substitute that will be minus a0 minus a1x etc. minus ad minus 1 x power d minus 1, and now rewrite this equation as a combination between x and 1 x square and x power d minus 1. So then this will belong to where we wanted. So I will just write this will belong to a plus ax plus a x power d minus 1. So that finishes the proof of inductive step, and therefore we proved that every element, every generator of this Ax is contained here, therefore this equality. Because every element is a polynomial in X, and we proved that all monomials belong to the right hand side, therefore a finite sum will also belong to that side. So that is it. Alright, so that proves 1 implies 2, and the last one left was 4 implies 1. And what is given? So 4 is given. Suppose that what was 4? 4 was there is a module M which is finitely generated over A. The module is finite as a module, that is as a module over A it is finitely generated. So we have elements x1 to xn, so that it is a module is generated by x1 to xn, and M is faithful as Ax module. So suppose that M is an Ax module with these two properties. It is finitely generated as a module over A, and it is faithful as a Ax module. This means annihilator of M as a Ax module is 0. That is the two conditions we are given, and from here we are looking for an integral equation for x. That means we are looking for a monic polynomial in x with coefficients in A which is 0. And now here is the point where we will imitate what in example I did Cayley-Hamilton theorem, we will imitate that. So it is a module over Ax, that means if I take x and there is a multiplication of x on M, because it is a module over X, in particular x times any element of M makes sense, it is a scalar multiplication by x. So for each generator this xj, j from 1 to n, when you multiply this x by xj. This is a scalar multiplication we have given, and these are the elements in the module, therefore this makes sense. And this I can again write it as a linear combination of x1 to xn. So we will write this as a sum. Sum is running over 1 to n aij xi, and this is true for every j from 1 to n. And now imitate. Therefore what did we get after this? So you saw, by as in the earlier proof, as in the proof of Cayley-Hamilton theorem, in the above example, we will get determinant of x times the delta ij minus aij. This is a matrix. This multiplied by that xj's, all of them, that will be 0. But now it is a faithful module, so it cannot annihilate m. Therefore this has to be 0. So this, if you like, again we have used Cramer's rule, and we have importantly we have used this assumption: since annihilator of m as a ax module, this is 0, and this is an element in the annihilator. This annihilates every j by Cramer's rule, as we have seen in the earlier example, and therefore this has to be 0 because this is a faithful module. And but what is this? This is, when you expand this determinant, this is a degree n polynomial and monic polynomial, and coefficients will come from some multiplications and additions from these aij's, and these aij's are elements in the ring A. So when you expand this will become x power n plus an minus 1 x power n minus 1 etc. plus a1x plus a0. This is 0, and we know that a0 to an minus 1, these are elements in the ring A. So this one is an integral equation of x over A. Over means the coefficients are in A. So that is x is integral over A. This is very economical and verifiable condition. Let me just show you again. Look at this. Look at this proposition. These are 4 parts. This is integral over A, and our definition says that it satisfies a monic polynomial with coefficients in A. And this one is really verifiable, whether Ax is a finite as an algebra or not. It is a finitely generated A module or not. And this too is very verifiable. So I will show you in number of corollaries now how it is used, this equivalence of this integralness which is given by this proposition. All right. So corollary 1. All right. So as usual, B is, let B be an A algebra. A is our fixed base commutative ring, and x1 to xn or x1 to xn, x1 to xr are elements in the ring B. If x1 to xr, all of them are integral over A, then the subalgebra of B generated by x1 to xr, this is, I will write in the bracket, this is the A subalgebra of B generated by x1 to xr. So that means it is the smallest A subalgebra of B which contain all these elements x1 to xr. Then this subalgebra is a finite A algebra. That means as an algebra over A, it is it's a finitely generated as a module over A. That means finite A algebra. So proof. R equal to 1 is precisely the case proved in the proposition. Precisely one implies 2 in the proposition. So therefore I will prove this assertion by induction on R. So proof by induction on R. Already R equal to 1 induction started. So I only have to prove the step from R minus 1 to R. So assume that R is bigger or equal to 2 and the assertion for elements x1 to xr minus 1. So that means we are assuming, that is, we are assuming this subalgebra of B generated by x1 to xr minus 1 is a finite A algebra. That is what we are assuming by induction hypothesis. And now to prove that Ax1 to xr, this is xr minus 1 and xr, this is a finite A algebra. But look here, you have A here and we have Ax1 to xr minus 1. This is contained here. This is given to be finite extension, finite A algebra. And then what we want to prove is the next one, Ax1 to xr minus 1 along with xr, we want to prove this is finite. This is what we want to prove, this is finite. But we have given this element xr is integral over, this element is integral over A. Therefore this will be integral over a bigger ring. Since xr is integral over A, it is also integral over A adjoint the subalgebra generated by x1 to xr minus 1. But then by r equal to 1 case, this extension is finite. Ax1 to xr minus 1, xr minus 1, xr is finite over A x1 to xr minus 1. And now it is, if this is finite, this will be finite. Because if this is, you take the generating system for this as this module and take the generating system for this module as a modulo array, and you multiply them, and then you get a generating system for the module for the A module, this upper one. All right. So I will just say therefore A x1 to xn xr is a finite A module by transitivity, I will say transitivity. This is very easy. All right. So now what we do is, if I have, okay, so if I have, so the next one, for I am preparing for the next one. So let B be an A algebra. That means you have a structure homomorphism phi from A to B, and already you have been writing elements and multiplying by elements in B. That simply means we are when I write A times x, what does this mean? This means phi A times x for A in A and x in B. This is what we have been writing. So this we may assume that this is actually a subring. So we may assume, in general, we may assume that A is a subring of B, and the inclusion homomorphism is the structure homomorphism. This is, if you like, replacing A by phi of A. And remember, when we say subring, that identity of the ring and identity of the subring, they are the same. All right. So next corollary, and now so whenever I have a, this is also called a ring extension. That means ring A and this ring B, and this ring is got extended. So the ring structure is same. The multiplication and addition in the ring A is a restriction of addition and the multiplication in the ring B. Okay. Now corollary, next corollary 2. So let A contained in B be a ring extension. Okay, then A bar is precisely by definition all those elements of the upper ring B, so x in B, such that x is integral over B, integral over A, contains A, and this is contained in B by definition, and this is a subring of B containing A. This A bar is called the integral closure of A in B. This I should write in the bracket. So what we need to prove that it is a subring. That means we need to prove that. So first of all, this inclusion is obvious, because if you have an element in A, how do we write down an integral equation for A? That is very simple. It just satisfies the equation A minus A. The coefficients are in the ring A. So this is obvious, and this is also obvious by definition. Now to prove that it is a subring, I have to prove that. So proof, for x y in the A bar to prove that x plus minus y and x dot y, they also belong to A bar. Once we prove that, it is subring is clear, because one is there, one of this and one of B is same, because A is a subring of B and so on. So, it is enough to prove this. Now, from here what do we know? That x satisfy a monic equation, y satisfy a monic equation over A, and we want to check whether x plus y, x minus y, x times y, they also satisfy a monic equation with coefficients in A. So, now if you try to find out by using the monic equation that x satisfies and that y satisfied, that will be very complicated. So, what will come in handy is the proof of equivalence of 1 and 2 in the above proposition. So, what do you have to prove? That, so look at this. So, A is here and x and y are elements in A bar. So, I consider the subalgebra generated by x and y. This is a subalgebra of B generated by x and y. And what do you want to prove? I want to prove that this is also contained in A bar. So, I will write in the red, this is what the proof we are looking for. This. That means what? We want to prove that every element of this is also integral over B, in particular x plus y, x minus y and xy. But what do I know? Since x and y both are in A bar, we know that this Ax over A, this is finite, and Axy is here. And like in the above corollary, if y is integral over A, y is also integral over this bigger ring. So, this is finite and this is also finite, because both are integral. Therefore, this will be finite. Once you know that, then if you take any z, so that will imply A is contained in Az, is contained in Axy, then this is also finite. Because if you like, you use 3 or equivalence of third one, that some element is integral if the subalgebra generated by that is contained in a bigger subring, which is also finite. So, that proves this inclusion. So, this inclusion is proved. So, therefore, we proved the corollary 2. Alright, now next corollary 3. Again, what is the setup? Let we have a ring extension like this, A contained in B and B is contained in C. B ring extensions. If C is integral over B, so when do I say extension is integral? That means every element of C is integral over B. So, I will write here once at least C, that is every element of C is integral over and if B is integral over A, again the same, that means every element of B is integral over A then C is integral over A. This should be called a transitivity of integralness. Transitivity of integral extensions. Proof. What do I need to prove? I need to prove that every element of C is integral over A. That is this. So start with an element in C. Let X belong to C. And what are you looking for? We want to show that this X satisfies a monic polynomial with coefficients in A. So that is what we want to show. And what do we know? We have given that C is integral over B. So that means since X is integral over B, it will satisfy a monic polynomial with coefficients in B. So we can write like that: x power d plus b d minus 1 x power d minus 1 plus b1x plus b0 equal to 0, with b0 to bd minus 1 they are belonging to B. But we want the coefficients to be in A. That is our aim. Alright. But now what do I do? A is here, C is here, and this X was an element there, and B was here, and all these B1 to BD are in B. So I can consider a subalgebra of B generated by this. So that is A B prime, let us call it B prime. This is the subalgebra of B generated over A by B0 to BD minus 1. It's clear from our notation that this is a subalgebra of B over A generated by B0 to BD minus 1. And this is obviously A is a subring here. So we are in this situation. And what do we know? B is integral over A. That is also given to us. That means every element of B is integral over A. That means all these BI's, B0 to BD minus 1, they are all integral over A. And therefore this will be a finite A module by corollary 2. So this one is a finite A module by corollary 1 or 2, 1. Alright, now what do you want to prove? Now if this is this X, now the integral equation of X has coefficients here, B0 to BD minus 1, so they are coefficients in B prime, because I put them in B prime. Further, X is integral over B prime, because I already know this equation, and B since B0 to BD minus 1 they are elements in B, and this equation is an integral equation of X over B prime. So that means what? So that means A is here, contained in B prime is here, contained in, now take the subalgebra of B of C generated over B prime by X. This is contained in C. This is finite because it's integral. This is finite, already we noted, and therefore that implies B prime X is a finite A subalgebra of C. So therefore I found AX, and AX is contained here. So therefore by condition 3, so I will write next, so therefore by the implication, by the equivalence of 1 and 3 in the proposition, it follows that X is integral over A, and that is what we wanted to prove. So that finishes the proof of the corollary 3. Now one more corollary, corollary 4. Now the situation is, let B be an A algebra. A is our fixed base commutative ring, then the following are equivalent. Okay, 1, this B is a finite A algebra. That means B as a modulo over A is finitely generated, and 2, B is of finite type over A, and B is integral over A. Proof. One implies 2 is trivial, because if some algebra is finite as a module, then it is finite type over A, and finite, then it is integral over A also, that we have seen in the proposition, if you like, equivalence of 1 and 3. Conversely, to prove that 2 implies 1, what is given? We have given B is finite type over A. So B is given to be as an algebra over A generated by finitely many elements, x1 to xr by 2, and these guys, all elements of B are integral over A, and x1 to xr are integral over A. Now from that it follows induction. So A is here, contained in Ax1 here, contained in Ax1 to xn, Ax1 x2 here, contained so on, contained B here, which is Ax1 to xr. At each stage it is finite. This is finite because x1 is integral over A, x2 is integral over A, therefore it is integral over A, therefore this is finite. So similarly so on. So all each stages, they are finite extensions, finite algebras. That means that the module over A is finite. So if you have a tower of ring extensions where each stage is finite over the earlier one, then the total B will be finite over A. So that you imply B is finite over A. So which is 1. So that proves the corollary. And then next time I will give number of examples. We will deal with examples, and also I want to then eventually study the spectrums. What is the properties when do you say extension is integral? What happens to the spectrum? So that is we will do it in the next lecture. Thank you very much. We will continue integral extensions in the next lecture.